We will now talk about isomorphisms. So let V and W be non-linear spaces and T from V to W linear 1, 1 and on 2. So in linear algebra, this would also already mean that it's an isomorphism between the two vector spaces. But now we are in the question of non-linear spaces, and therefore we say that T is an isomorphism if both T and T inverse are continuous. So then you say, so whenever we talk of isomorphism in the context of non-linear spaces, we mean a 1, 1 on 2 linear map which is continuous and the inverse is also continuous. Okay, so given two norms on a vector space, we say norm 1 and norm 2. I am putting a bracket now because so that we don't confuse with the norm 1, norm 2 which we defined earlier. Okay, so norm 1 and norm 2, we say that they are equivalent if they induce the same topology on V. So this means that if I have V with norm 1 and I have V with norm 2, we have two non-linear spaces, and you look at the identity map between these two spaces. So every open set here, the inverse image is the same thing and it has to be open here, and every open set here, the inverse image is the same as it has to be open here. This means the two topologies are the same. So if and only if I is an isomorphism. So the norms are equivalent if and only if I is an isomorphism. So this means that we have that norm x 2 is less than or equal to some k1 times norm x1 for all x in B, and norm x1 is less than some k2 times norm x2. For all x in B. Therefore, we can say for all x in B, we have that norm of x1 is less than or equal to some or rather c1 times norm x1 less than norm x2 less than or equal to some c2 times norm x1. So this is a necessary and sufficient condition for two norms to be equivalent, which means of course that the topologies are the same, or in other words that the isomorphism is identity map is an isomorphism. So let us look at some examples. So let us take Rn with the norm 1 and norm infinity. So what is norm 1? So norm x1 equals mod x1 plus mod xn, and norm x infinity is max mod xi 1 less than or equal to I less than or equal to n. And therefore, we have that norm x infinity is certainly less than or equal to norm x1, and norm x1 is less than, so each one is less than the maximum, and so this is less than n times norm x infinity, and therefore these two norms are equivalent. Now let us look at norm x1 and norm x2. So norm 1 and norm 2. So we have, what is norm 2? It is sigma mod xi square power half. That is norm x2. So we have that sigma mod xi square is always less than or equal to sigma mod xi whole square, because the cross terms are missing, only the squares are there. Therefore, from this it immediately follows that norm x2 is less than or equal to norm x1. But norm x1 you apply the Cauchy-Schwarz inequality, so this will be less than or equal to root n times norm x2. So these two norms are also equivalent. So norm x1, norm x infinity and norm x2, they are all equivalent norms, because equivalence is of course a transitive condition. So now let us, what is the usual topology on Rn? Rn, the usual topology, you take a neighborhood is nothing but a ball, and this is given by the norm 2. So norm 2 gives you the usual topology, and therefore norm 1, norm infinity also give the same topology. We know that because the ball for norm infinity has the following shape, and the ball for norm 1 has the following shape, and therefore inside any ball of one of these three kinds you can put any other smaller ball at every point, and therefore the topologies are the same. So the usual topology, in particular we have that every bounded and closed set is compact, and this is a very important fact to remember, and we will use this to show. So we now saw that norm 1, norm infinity, norm 2 are all equivalent. In fact, it turns out that in a finite dimensional space all norms are equivalent. So this is a very beautiful theorem which we will now prove. So theorem, V finite dimensional vector space, all norms on V are equivalent. So proof. So recall the notation we had, Ln1 is nothing but the space Rn with the norm 1. So V is a vector space, finite dimensional, dimension V equals n, say, and given some norm. So we will show that these two are isomorphic. So we claim V is isomorphic to Ln1. So whatever be the norm on V, we show that it is going to be isomorphic to Ln1. So now if you have assumed the claim, then if you take V with two norms, so we have V with norm 1, V with norm 2, and then you have Ln1. Now we will show that this is isomorphic, this is isomorphic with the same map, and then we will show therefore the identity map here is also going to be an isomorphism. That will be the idea of the proof. So proof, so let E1 En be the standard basis of Rn. Fix a basis V1 to Vn of V, and you define T of Ei equals Vi and extend linearly. So then we already saw in the earlier example that T is continuous. And also we know that T is 1, 1 and onto because it maps a basis into a basis among spaces of the same dimension, and therefore we now want to show that T inverse is continuous. So assume not. Then we saw that if continuity is the same as continuity at the origin, and therefore it is not continuous at 0. What does this mean? There exists a yn converging to 0 and an epsilon positive such that T inverse of yn in norm is bigger than in norm 1, because that's this thing. So T is where? T is from ln1 into V. So there exists a yn which goes to 0. So T inverse yn in norm 1 is bigger than epsilon, which is bigger than 0. This is the contradiction, contrapositive statement of the fact that it is not continuous at the origin. So now let me define Zn is equal to yn by norm T inverse yn 1. Now T inverse yn in norm is bigger than epsilon, so the denominator is staying away from epsilon, and therefore Zn will also converge to 0 in V. Now what about T inverse Zn? Norm of T inverse Zn is 1, because I have divided by the correct number, and therefore norm of T inverse Zn is 1. So T inverse Zn is a bounded sequence, and you know, therefore since the ln1 norm, the norm 1, norm 2 are all the same, that's the usual topology in Rn. So if you have a bounded sequence, then it has a convergent subsequence. So there exists a convergent subsequence T inverse Znk. Let us say it converges to x. Then this implies that norm x is equal to 1. But what about Tx? Tx is the limit of T inverse, T of T inverse Znk, which is Znk, limit of Znk, and that is 0. So Tx equal to 0 and norm x equal to 1, which is impossible since T is 1, 1. Therefore contradiction. Consequently, T inverse is also continuous, and therefore, as I said, we have here V with norm 1, V with norm 2, and the identity map between the two, and then the same map T from ln1, which is an isomorphism. So the identity is a composition of T inverse and T, or T inverse and T in these ways, and therefore you have that the identity map is an isomorphism in both ways, and therefore therefore we have that identity map is an isomorphism, and consequently all the norms are equivalent. So this is not true in infinite dimensions. So this is example, not true in infinite dimensions. So let us take an example of C01. We can construct many such many examples, but anyway, so we have the usual norm. So norm f is max mod ft 0 less than equal to t less than equal to 1. Now I am going to define norm f1 here to be integral mod ft dt. You can check that this is a norm. So this is very easy to check. Triangle inequality is also trivial, and therefore this defines a nice non-linear space. Okay. I claim that these two are not equivalent. Now first of all, norm f1 is mod ft dt. I pull out the mod ft as a supremum, so this is less than equal to norm f into integral 0 to 1 dt, which is just 1, and therefore you have this. Now what about the reverse inequality? Can you write norm f less than equal to c times norm f1? Is this possible? Answer is no. So we can give a counter example. We can construct several. There's one in the book which I mentioned to you, and now I will give you another one. So let us take fn equals t power n, same fn t as t power n. Then what is norm f n? It is 1 for all n. What is norm fn 1? Well, it's a non-negative function, therefore it's just the integral, which is therefore 1 by n plus 1. So if you put fn here, you will get 1 on this side and 1 by n plus 1 on that side, which goes to 0, and therefore this inequality is not possible, and consequently you cannot have, so you cannot have the equivalence of norms. So in infinite dimensional spaces you do not have the equivalence of norms. Now the equivalence of norms followed from the main thing which we used in proving the equivalence of norms is that the unit ball or bounded and closed sets were compact. Now this in fact characterizes finite dimensional spaces. This is a very amazing fact. The dimension is something which is purely algebraic. It says what's the maximal linearly independent set. So that is a completely algebraic statement. On the other hand, the compactness of the unit ball is a topological statement, and these two are connected by this theorem. So we have the very beautiful result that, so theorem. So B equals set of all x in B, norm x less than or equal to 1, where V is a non-linear space. So B is compact if and only if V is finite dimensional. So before we prove this, we need a lemma. So we have a lemma due to these. Okay, so let V be a non-linear space and W contained in V a closed and proper subspace. So given epsilon positive, there exists a u in V such that norm u equals 1 and the distance of u from W is greater than or equal to 1 minus epsilon. So what is the distance of x from W? This is nothing but the infimum of norm x minus y, the distance of x for all y in W. So it's the shortest distance which you can come from x to W. So the Riesz lemma says that you have a closed and proper subspace, then you can find a vector u which is a unit vector such that du W is bigger or equal to 1 minus epsilon. So let us prove this statement first. So W is proper. So there exists a V in V minus W. And let us take delta will be the distance of V from W. W is closed. So this has to be strictly positive. So this is because W is closed. Okay. But what is delta? The distance is nothing but the infimum of something. So there exists. So choose W in W such that delta is less than or equal to norm of V minus W. That's always true. But then because it's an infimum, it can be made less than or equal to something slightly bigger. So I will put delta by 1 minus epsilon. 1 minus epsilon is less than 1. So this is slightly bigger than delta. So between these two we can always fix in a W. Okay. So now put u equals V minus W by norm of V minus W. Then u, of course, norm u is 1. So that is already true. So let us check that the other property is true. Okay. So let Z be an arbitrary element in W. So what is norm of u minus Z? Norm of u minus Z is norm of V by V minus W by norm of V minus W minus Z, which is equal to V norm of V minus, I am going to club all the terms, it says W plus norm V minus W times Z, the whole thing divided by norm V minus W. Now W is in W, Z is also in W, W is a linear space, so the whole thing belongs to W. So V minus any element in W is at least greater than or equal to delta, we know that, and norm of V minus W we just saw is less than delta by 1 minus epsilon. Since it's in the denominator, this is delta by 1 minus epsilon, which is equal to 1 minus epsilon. Therefore, norm of u minus z is greater than or equal to 1 minus epsilon for any z in W. Therefore, du W is greater than or equal to 1 minus epsilon. So this is the proof. Okay, so now we will prove, proof of the dimension theorem. Namely, by this I mean unit ball is compact if and only if the space is finite dimensional. So now let us assume V is a finite dimensional non-linear space. So let B be the closed unit ball. Now T, let us take, is the mapping which we defined early, T ln1 to V, where n is the dimension of V. We saw that this was an isomorphism. Okay. So B is a closed unit ball. So T inverse of B is bounded and closed, therefore compact in ln1. Therefore continuous image of a compact set is compact. So B is T of T inverse B, and therefore B is compact. So this shows that if you have a finite dimensional space, the closed unit ball is always compact. This is of course expected. Now let us do the converse. So let B be compact. So to show V is finite dimensional. So B is compact, therefore there exists some x1 xk in B such that the ball center xi, radius half, covers B. Okay. So because you take all balls like this, that forms an open cover. There is a finite subcovers which I have extracted, and therefore you can find a finite number of points in B such that if you take the radius this. So I claim V is nothing but the span of x1 to xk. So this will prove, this shows that the dimension of V is less than or equal to k, which is finite. We can't say it's equal to k because we don't know if these are linearly independent or not, and therefore, but that we don't need that. We just have to show that this is the same. So let us assume not. Assume not. So W equals span of x1 to xk is a proper subspace of V. So this is finite dimensional, and therefore, okay, so W is finite dimensional. Now, so W is finite dimensional. What does it mean? Every finite dimensional space, all norms are same, and therefore every finite dimensional space is complete. And since it's a complete subspace of a norm-linear space, it is closed, implies W is closed. So from the equivalence, so all norms, so remark, all norms on a finite dimensional space are equivalent. This implies that W finite dimensional spaces are always complete. And this again implies if W is contained in V, W finite dimensional, then W is closed. Because it has to be complete, which means every sequence converges within itself, and therefore it is closed. So W is closed, it is proper. Therefore, by the Rees lemma, there exists a U in B, norm U equal to 1, that's of course there, and in fact we have this, and D of UW is greater than or equal to 3 by 2, or 2 by 3, see. But this is a contradiction. In particular, d of u from xi, which is norm of u minus xi, is greater than or equal to 2 by 3. But the entire B is contained in the union of the balls of radius half with center xi, so this is a contradiction. Therefore, the claim is established and we have shown that this is true. So, a finite dimensional space is characterized by the compactness of the ball. So, in infinite dimensional spaces, the unit ball or a closed bounded set is never compact. So, let us check in an example explicitly. Let us take little L2. So, this is a set of all sequences xi such that sigma mod xi square is finite. So, let me take ei to be the sequence which is 0, 1 in the ith place, 0 everywhere. Then what is norm ei minus ej 2? So, you will get 1 in the ith place, a minus 1 in the jth place, and therefore this will be nothing but square root of 2. So, this means each element is at equal distance from all other elements. Therefore, ei does not have a Cauchy subsequence, that is ei does not have a convergent subsequence. Therefore, unit ball in L2 is not compact. Because if it were compact, then every bounded sequence must have a convergent subsequence, and so this is an example where this is not true. So, we have proved this, we have directly verified, but we know from the theorem which we just proved that space, the unit ball will be compact if and only if the dimension is finite. L2 has of course infinite dimension, and therefore it is not